Now, next point to compare the common base configuration and common emitter configuration is current gain. In common base configuration, we have studied about current gain, that was alpha, and that was representing the ratio between del IC upon del IE, and we have calculated alpha that is always less than 1 because del IE is equal to del IC plus del IB. That's mean IC change in collector current is always less than change in emitter current, so that's why its ratio will be less than 1. And in common emitter configuration, current gain was defined as beta, that was IC upon IB, or for beta AC, change in collector current upon change in base current, and beta is 2I, beta is larger than 1, always larger than 1. It's mean that IC is greater than IB. In each cases, IC is in milliampere while IB is in microampere, so that's why beta is greater than 1. So we can say that the current gain in common base configuration is less than unity. Current gain in common base configuration, that is alpha, is always less than unity, the closer to this value for unity. The current gain is quite high for common emitter configuration, and its value may be nearly 250. The high current gain makes it possible to have transistor as an amplifier with the high voltage as well as high power gain. So that's why we will select common emitter configuration as an amplifier because its current gain is greater than unity. And we have discussed in our lecture that common collector configuration cannot be used as an amplifier, but it can be used as an impedance matching device. So for making amplifier, we always prefer common emitter configuration. Next point for comparing the common base and common emitter configuration is transconductance. Transconductance. See, this term is made with the help of two words, trans and conductance. Everybody know that conductance is the ratio between current to the potential, but transconductance, that's when transfer of conductance, is the ratio between output current to the input voltage. Ratio between output current to the input potential. So in case of common base configuration, for common base configuration, transconductance GM is defined as output current. Output current is collector current and input potential is VEB, emitter base potential. And in common emitter configuration, the ratio of the change of the collector current to the change in base emitter voltage, keeping the collector voltage constant. So that's why GM in common emitter configuration is equal to change in IC upon change in base emitter potential at constant Vc. It can be written as change in IC upon change in IB into change in IB upon change in VBE. From this point, see, del IC upon del IB represents the term beta, and del IB upon del VBE is the input conductance of base common emitter transistor. So it can be written as beta upon R input, because this is the representing the conductance, input conductance. So that's why it is represented as beta upon R input. So common emitter configuration has the transconductance of beta time of R input, and this is the R input in common emitter configuration. Now leakage current. Next topic to compare is leakage current. Leakage current. In case of leakage current, the leakage current due to flow of minority charge carrier. As the majority charge carrier increases with the temperature, the leakage current increases with temperature. The leakage current in common base configuration is very small. In common base, configuration, leakage current is very small. Maybe its order will be of milliampere or microampere. From calculation it will be of order of microampere, and leakage current in common emitter configuration is higher. In common emitter configuration, leakage current is higher. The larger value of leakage current in this mode is its disadvantage. That's when, if the value of leakage current is higher, then it will not be beneficial to use that configuration. But due to several advantages of common emitter configuration, we will use it as an amplifier and as a switch. Now voltage gain. The voltage gain is the ratio of output upon input. Then in the case of common base configuration, voltage gain is AV is equal to V output upon V input. Here it will be in common base configuration, it can be written as output voltage is equal to I output into R output upon I input upon R input. So that's why ratio will be of alpha into R output upon R input. While in case of common emitter configuration, it will be equal to beta into R output upon R input. But it will be negative. We will discuss why it will be negative. See here, the magnitude of voltage gain in common base configuration is alpha R output upon R input, while in common emitter configuration it is equal to minus beta into R output upon R input. Everyone know that alpha is less than 1, so that's why here voltage gain is less than 1, less than input voltage, less than 1, and here beta is greater than 1, so that's why voltage gain in common emitter configuration is larger, but its polarity will be negative. That's mean the output voltage will be in different phase of input. Now some parameter of configurations. We have taken common base configuration, common emitter configuration, and common collector configuration. Our first parameter is input dynamic resistance. Input dynamic resistance. For common base configuration, input dynamic resistance is very low and common collector configuration is low. We will neglect the common collector configuration because there is no need to study about common collector configuration. It will be of magnitude 50 ohm, 49 ohm, and it will be of 1 kilo ohm. That's mean input resistance of common base configuration is less than the common emitter configuration. Output dynamic resistance. Output dynamic resistance very high and it's as high. Very high, it will be of 1 mega ohm and it will be of order of kilo ohm, 10 kilo ohm. Current gain AI, this will be current gain will be less than unity while current gain is high. Here the current gain is beta and here current gain is alpha. So current gain in common base configuration is less and common emitter configuration is higher. Leakage current. Leakage current very small and very large. Voltage gain AV, here voltage gain is small while here voltage gain is large. Input resistance for common collector very high. Output resistance are dynamic low and so on. So in common base configuration the input dynamic resistance is very low, that will be of 50 ohm, but in case of common emitter it is low, that's means the higher than the common base, that is of kilo ohm, while in the common collector it will be very high. The output dynamic resistance is very high in common base configuration, while in case of common emitter configuration it is high, that and current gain is less than 1 in common base, while current gain is common emitter is high. Leakage current is very small in common base, very high in common emitter, and voltage gain is small in common base while larger in common emitter. So from this point of view, input dynamic resistance is low, output dynamic resistance is high, current gain is high, and voltage gain is also large. These factors make common emitter configuration more useful than other. So that's why mostly we will use common emitter configuration for the operation of our devices. Thank you.